Okay. Hi, everybody. This lecture will talk about the material balance. Previously, we show you example, like degree of freedom analysis to make like the balance, but we focus on only the one unit. But this slide we talk the multiple unit because in most industry, in chemical and petrochemical industry or polymer industry, there are more than one unit process involved in the plant's environment. For example, in reactor, to make like the from reactant to the product. We do not have only one unit, but there are sometimes the mixing reactant. That's why mixing reactant we call this unit, one unit process, and blending of product. And also we have some heating or cooling process, and also you have some separation process. That's why. For example, we have like reactor. That's right. And also we have some the mixture of reactant. That's right. If we have one or two reactant, you have reactant one, reactant two, mixing, and then you feed to the reactor. Feed to reactor. If reactor is exothermic reaction with the system or temperature inside the reactor will increase. You have to control the temperature to constant. You have to reduce the temperature of the reactor by you have to add like some cooling process. You have to add the cooling coil. You have to add the jacket to decrease the temperature. And also after the reaction, in the reaction there are some mixtures, the unreacted reactant product. If you would like to get product, you have to some separation unit, and then you get product. And maybe you have some unreactant, that's right. And also you can spit out or you can recycle to mix with this. That's right. You about the recycle for the next week, okay. But for this case, we talk only the multiple unit. That's right. For multiple unit. That's right. It's maybe you can balance around the mixing, you can balance around the reactor, you can balance around the separator, or you can balance the overall process. You can balance with the mixing and reactor. You can balance reactor and separator. You can separate. If you balance overall, you cannot solve for the problem. You can balance for each unit. That's right. I will talk to you how to do this step by step. For this example, right, we have about 1B is the mixing point between feed 2 and feed 1 mixture. And send to unit 1. For unit 1, you get product 1. And send product out unit 1. You get a split. This is product 2. That is separation unit. And you send to unit 2, you get feed 3 and product 3. That's right. For mixing at point B, we have two feed streams, right? Feed 1 and feed 2. And one product stream. And unit 1, we have one stream input and two stream output. For this point, we have one stream input and two stream output. And unit 2, we have two input and one output, for example. Okay. The dashed line is the unit, right? You can balance around the mixing. You can balance around unit 1. You can balance around this. You can balance around this. Or you can balance overall. That's right. You can balance overall. It's up to the process that we have some information. It for give you an example, right? The basic for calculation or the procedure for material balance calculation is the same as single process. The difference is the case you may isolate and write balance on several subunits. I talked you can run the mixture, you can run a separator, you can run unit 1, you can run unit 2. Run unit 2 to obtain the enough equation to determine all unknown stream. And also you have to carry out degree of freedom analysis at the same as you about the single unit process. You can carry out degree of freedom overall process or in each unit or a mixture of units. Or mixture of units. You cannot write and solve equation for subsystem until you have verified it has zero degree of freedom. That's right. In conclusion, you have to verify that the subsystem or the overall balance it should be zero degree of freedom. You have to verify this first. That's right. For example, okay. Right. For example, we have two unit like it's a continuous steady state, two unit process is shown below. For this case, steady state there is no accumulation. That's right. Accumulation. For this case, there is no reaction. Okay, input equal to output. Right. For each stream contain two components A and B in different proportion. That's right. Okay. Three stream host flow rate and composition are not known. Stream 1, that's right, the output from unit 1. Stream 2, that's right, after mixture with this feed. Stream 3, output of unit 2. This is the unknown stream. 1, 2, 3. That's right, this you know the feed. You know output this. You know this. You know this is the unknown 1, 2, 3. These are multiple units. That's right. Okay. And then for basic, we given the flow rate. Okay, you know the feed flow rate. Total mass, you know feed output for this. It's 1, 2, 3. You have 1, 2, 3 is unknown. You have to specify M1 is the mass flow rate output unit 1. X1 is the mass fraction of A. And mass fraction of B calculated by 1 minus X1. X2 is the mass fraction of the product after mixture stream 1 and this stream. 1 minus X2 is the fraction of B, and M2 is the total mass flow rate of stream 2. And also stream 3 specify M3, total mass, and X3 is the mass fraction of A. 1 minus X3 is mass fraction of B. Okay. For this case, you specify and you draw the flow chart completely. That's that. You know the mass flow rate for each stream with known and unknown. You know the fraction of A and B for each stream with known and unknown. That's right. And then you have to done the degree of freedom analysis. That's right. For this case, you can degree of freedom in with overall, and allow unit 1, allow midpoint, allow unit 2. For this case, the first step, you done the overall balance, overall system. For this case, this is the overall system. Okay, you count unknown. For this overall, we have 1, 2, only 2 unknown. That's right. Only 2 unknown. M3 and X3, and also we have 2 species, A and B. You can use 2 independent equations. For that case, we have degree of freedom equal to 0. That's right. For the overall system, you can balance based on A, you can balance based on 2, and then you solve for M3 and X3. Because the degree of freedom is 0. Okay. For overall, you can solve for M3 and X3. For mixing point, okay, is the mixing point. How about unknown mixing point? M1, X1, M2, X2. We have 4 unknown. For this case, 4 unknown, but we have only 2 species. 4 minus 2 equal to 2 degree of freedom. For this case, you cannot solve the mixing point. You cannot solve the mixing point. Okay. The next step, you consider the unit 1. Unit 1. This unit 1. You know input, you know output, and you don't know stream 1 with M1 and X1. For this case, 2 unknown. That's right. 2 unknown and only 2 species. You have 2 unknown minus 2 equations. You get 0 degree of freedom also. That's right. For unit 1, you can solve M1 and N1. M1 and N1. And then you back to the flow chart. You know M1 and N1 from this. You know M2 and M3 from overall. And the remaining is M2 and X2. M2 and X2. For this case, you can balance unit 2. That's right. If you balance unit 2, we have M2 and X2 is unknown. Because M3 and X3 you know already. You can solve for M2 and X2. Or you can balance around mixing point. For this case, M1, X1, you know already from balance around unit 1, and then you can solve for M2. It's up to you. You can choose mixing or two. That's right. Mixing or two. For this case, I show mixing point. The mixing point now only two unknown, M2 and X2, because M1, X1 you know already from unit 1. And then you have two balance equations, you get degree of freedom. That's right. It's very important you have to check the balance overall for each unit. That's right. If the balance is degree of freedom is equal to 0, that means you can solve for that. For this process, the first step, you have to balance overall. After you balance overall, you know M3 and X3. And the second step, you balance around unit 1. You know M1 and X1. And the next step, you can balance mixing point or unit 2. You can solve for M2 and X2. Okay. The next step, you degree of freedom analysis already, and then you construct the material balance. For this case, I show you again, this is the general balance equation. It's input minus output plus generation minus consumption equal to accumulation. For continuous flow, flow rate of input or output is the mean like no accumulation. No accumulation. And they, for this system, no reaction. Okay, no consumption and no generation. You get input equal to output. That's right, input equal to output. And then you next step is calculate. The first step you calculate based on overall balance, right? To solve for M3 and X3. For overall balance, the first step you balance based on total mass balance. Total mass balance overall, we have two input. That's right, 100 kilogram for this steam plus 30 kilogram per hour on this steam equal to 40 plus 30 plus MT. That's right. 100 plus 30 equal to 40 plus 30. You have to specify unit also. 100 plus 30 kilogram per hour equal to 40 plus 30 kilogram per hour plus MT. Then you can solve MT. The next step you solve for X3. That's right. X3 you have to solve the A balance. That's right. A balance, how about A input? A input for this steam is 0.5 kilogram A per kilogram total multiplied by 100 kilogram total per joule over. That's right. 0.5 multiplied by 100, and this 0.t multiplied by 30 equal to 0.9 multiplied by 40 plus 0.6 multiplied by 30 plus xt multiplied by mt. That's right. This case, yes. This also unit is kilogram per hour. This is, and this is M3, that's right, and you can solve for XT. Okay, for this, the next step, you have to balance around unit 1. For unit 1, the total mass around unit 1. This is unit 1. We have one input is 100 kilogram per hour. We have two output is 40 kilogram per hour plus M1. That's right. 100 plus 40, you get 100 equal to 40 plus M1, you can solve for M1. That's right. You can solve for M1. And then you balance A balance, and you can balance A or B, it's up to you. Easy can be balance on A. A balance, A input 0.5 plus, 0.5 multiplied by 100 is the A. That's right. Kilogram A per kilogram total multiply kilogram total per hour, you get kilogram A per hour. And output 0.9 kilogram A per hour multiplied by 40 kilogram per hour plus X1 multiply M1. You know M1, you can solve for X1. That's like this. You can solve for X1. The next step, for this case, you know M1, you know X1, you know M3, you know X3, you can solve each other, right? Mixing point or unit 2. For this case, you solve for mixing point. Okay, back to the future. It's mixing point. Total mass is M1 plus 30 equal to M2. M1 you know already. You can solve for M2. That's right. You can solve for M2. M1 plus 30 equal to M2. You know M1, you can solve for M2. And then you solve for A balance. A input is x1 multiplied by m1 equal to x2 multiplied by m2. You know m1, you know m2, you know x1. You can calculate x2. Yes, you can calculate x2. Okay, it is a example for calculate like the multiple unit process. In where top you, the first step you have to choose the basic, you have to draw the flow chart, and then you have to check the degree of freedom, right? You check the overall balance, the unit, and sometimes you can mix. For this example, you have to, the first step, you make the overall balance, and then you make the balance unit 1, and then you make unit 2. For this case, you make overall, you know M2, M3, X3. Then you make unit 1, you know M1, X1. And then you make a mixing point, you know M2, X2. And you know M1, X1. Okay. This is the example. For another example, right? This example, we talk about an extraction distillation process. Extraction distillation process. We have a mixture containing 50% by-weight acetone and 50% by-weight water. Is 50% A acetone and 50% weight water. Right. It to be separate into two streams. Into two streams. One is in acetone, the other in water. You have to separate. This is water. This is acetone. This is acetone. We use this extraction. We add like M solvent. The separate process consists of extraction of the acetone from water into methyl isobutyl ketone MIBK, or we stand for is M. Right? We mix feed with M. For this case, acetone will transfer to M. That's right. Acetone to transfer to M. The mode phase after the extraction, and then you keep for setter. That's right. Setter. And then the bottom is mode M and A. The upper phase is mode water and A. That's right. Water and A. And then you mix again. You add a new solvent M. Mix with the raffinate. We call it the upper phase is raffinate and lower phase is extract phase. So you mix solvent with raffinate, and then you keep settle. That's right. The top phase is raffinate 2. The bottom is extract 2. Extract 2 and extract 1 mixture, and then send to distillation column. That's right. This is the mixture of combined extract 1 and extract 2, and then you send to the distillation column. And raffinate 2 you send out. That's right. Been sent out. It consists of this component. And then the product of distillation will consist of two products, top product and bottom product, with show the component for each case. Right. Did it show you the problem statement? You can read it and you can summarize in this. You can summarize in it. Okay. For the first extractor, this is include like mixing and setter. This is we combine together. We combine mixer and setter with extractor 1. We call it extractor 1. And also we combine mixer and setter. This is extractor 2. That's right, extractor 2. Okay. From this statement, we conclude in this flow chart that we have 100 kilogram of feed. 100 kilogram of feed. Yes. 100 kilogram of feed to the first extraction step. We add 100 kilogram of M. Mix together. That's right. Mix together. And then the output we have two streams. This is raffinate phase 1. This is extract phase. In the raffinate phase, we don't know the composition of the mass of acetone, M, and water. We denote by Ma2, MM2, MW2. That's right. This is the mass of acetone, M, and water. And the product extract phase is M1 is the total mass, and also we know the mass fraction of acetone in this phase. It's a mass fraction. This is 27.5 weight percent acetone. That's right. And also we specify XM1 is mass fraction of M. Mass fraction of M. And then mass fraction of water equal to, we have three components A, M, W. As you know, A is equal to minus 0.275. That's right. Is 1 minus 0.275 minus X M1. That's right. You get this 0.725 minus X M1 is water. Okay. For this case, we denote X M1 is mass fraction of M. And mass fraction of acetone we know from the problem statement is 0.275. And then you can calculate mass fraction of water in terms of M. That's right, because you know the total mass fraction is 1. That's right, 1 minus 0.275 minus XM1 equal to mass fraction of water, which is equal to 0.725 minus XM1. Okay. And next you consider like extraction 2. Or extraction 2, the feed M is 75 kilogram. It is 75 kilogram feed to the second step. The definite feed include 43 kilogram. That's right. 43 kilogram, which consists of this percent. That's right. 5.3% acetone, 1.6 M, 93.1 water, which is the mass fraction. It is 0.053 0.016 of M and 0.931 of water. This is the definite weight. And the exact weight M2 is the total mass of exact weight. And the exact weight is consists of 9% acetone, 8% M, and 3% water. That's right. 9% acetone, 88% M, and 3% water. This expressed in mass fraction. Okay. M1 and M2 mix together at this point, mix together, and then the output from mix is MA4, MM4, MW4. We don't know this mass. Is it MA is mass acetone, M is mass of M, and is mass of water, and then send it to the column, distillation column. The top product is M5. Right. The M5 we know the composition. Okay, the overhead product of distillation contain 2% M and 1% water. 2% M is 0.0 and 1% water is 0.01, and another one is 1 minus 0.01 minus 0.02, you get 0.97. But total is 1. But the bottom product, we don't know the composition, we don't know the mass. Okay, we denote as MA6, M6, MW6. That's right, for water M for acetone. That's right, this is the flow chart. That's right, you write all known and unknown information in the flow chart already. The next step, you have to consider the degree of freedom. The first step, you have to make overall balance. Overall. That's right. We have 3 input for this. For input is known amount. That's right. For about output, we have 1 output, 2 output, 3 output. This is known value. This is unknown one, M5. A6, M6, V6, we have 4 unknown. That's right. We have 4 unknown for overall balance. M5, MA6, MM6, MW6. And only we have 3 species. That's right. 3 species. Balance. That's right. On acetone, water, and M. Okay. 4 unknown minus 3 dependent balance equation, you get 1 degree of freedom. For that case, you cannot solve overall balance because there is 1 degree of freedom. And then we check with first extractor. For first extractor, right? The feed, we have 2 feed. This is known feed. This known feed. The output we don't know M1. We don't know XM1. We don't know MA2, MM2, MW2. We have 5 unknown. Right? We have 5 unknown. And also we have 3 species. Then we have 3 independent equations. Phi minus t equal to 2. 2 degree of freedom. You cannot solve the first extractor. That's right. Oh, you cannot. First extractor you cannot. Okay, the next we check with the second extractor. The second extractor, we have true feed also. With stream list, we have unknown MA1, MA2, MM2, MW2, 3 unknown. It is known value. And M3, that is known. Okay, we have 2 output and 2 feed. 3 unknown from feed and 1 unknown from output. We have 4 unknown. That's right. 4 unknown and 3 balance equation, 3 independent equation. Okay, we have 1 degree of freedom. You cannot solve second extractor. You cannot solve first extractor. You cannot solve overall. That's right. The next step, you check with mixing. Okay, overall, okay, you cannot. Extractor 1 cannot. Extractor you cannot. And then you can check mixing. In mixing, we have 2 input. That's right. This M1 and M1 is unknown. 2. MT 3. M4, MA4, M4, MW4 is unknown. Okay. 1, 2, 3, 4, 5, 6 unknown. And also 3 independent equation. You get 2 degree of freedom. You can solve this. The next step we consider the iteration column. Iteration column. We have 1 feed, 3 unknown. MA4, MM4, MW4. And 2 output, we have M5, MA6, MW6, M6, 3, 3, 6, and 1 is 7 degree. That's also 7 unknown. We have 7 unknown, but we have only 3 independent equation. Okay, this is 4 unknown. You cannot solve. You cannot solve. For this case, it is difficult. It's not the same like previous example. Previous example, you can solve overall, and then you can solve for each step by step. For this case, we check all of this. Overall cannot. Right. For each step cannot. Except 1 cannot. Except 2 cannot. Mixing cannot. Iteration cannot. This you cannot solve now. Okay. And the next step, we can mixture. You can mix between unit process. For that case, 2 extractor. Okay. Now we will make 2 extractor. Okay. Sorry. And then the next step, you can balance allow 2 extractor. That's right for this case. 2 extractor. Okay, this color. Okay. This is. Okay. For this case, we have 3 input. That's like 100 kilogram, 100 kilogram, and 75 kilogram. This is the input. That's right. And we have 3 output. This is output. This output. This output. That's right. For input, there is known value. Okay. How about output? We have M1, M1, XM1, and M3. That's right. We have 3 unknown. M1, XM1, M3, and this known value. Okay. For this case, 3 unknown. We have 3 species or 3 independent equations. You can solve for this. That's right. It's good luck because the true extractor, if you balance around 2 extractor, we have 3 unknown and 3 independent equation. We get 0 degree of freedom. That you can solve for this. That's right. Okay. The solution is after you check all of the solution is the first step. You have to analyze 2 extractor subsystem. That's right. You can write total mass balance or acetone balance or water balance or M balance. You can solve for that. That's right. And then after you know M1, XM1, and M3, that's right. M1, XM1, and M3. After you can solve around extractor 1 or mixing point. Because if you balance around the extractor 1, okay, you know M1, you know xm1, but now it's only 3 unknown and 3 balance. You can solve for this. And also, if you want mixing point, you know m1, xm1, you know m3, and then you can balance this. You can solve for this. You can solve for this. Okay. For this case, you balance 2 exactor first, and then balance the mixing. Mixing. You can solve for MA4, M4, MW4. And then you can solve for MA2, MM2, MW2. You can balance around first exactor or second exactor separately. And then you have remaining 4 unknown. M5, MA6, M6, and MW6. For this case, you cannot solve for that. We have only 3 independent equations with 4 unknown. For this example, you cannot solve for M5, MA6, MW6, MM6. Okay, you cannot solve for this. Because we have only 3 equations and 3 degree of freedom, and also we will be able to solve this problem. You cannot solve this problem. Okay. The first step, you have go back to the input, output, generation, minus consumption, and accumulation. For this case, it's continuous process. Accumulation no, consumption no, no relation. We get input, output. The first step, you run around 2 exactor. 2 exactor. Okay. Total mass balance 100 part 100 part 75 equal to M1 plus MT plus 43.1. This first equation. 100 plus 100 plus 75. This kilogram equal to M1 plus M3 plus 43.1. And then your balance is A balance. A balance. That's right. A input is 0.5 multiplied by 100. That's right. There is no A in this system. There is no in this system. Okay, we have only one input A. It's 0.5 multiplied by 100. And output A is, for this case, is M1 multiplied by 0.275 plus 0.09 M3 plus 0.053 multiplied by 43.1. That's right. This is M1. This is input. This is output from the first exactor. This is output from the second exactor. That's right. We have 2. Okay. For this case, we have 2 equations, 2 unknown. That's right. 2 equations, 2 unknown. You can solve for M1 and M3. You can solve this simultaneously. Okay. And then you can balance on M balance. That's right. If you balance on M balance, you can also multiply X M1. That's right. For M balance, M input 100. M input is 75. Is 100 plus 75. There is no this. Equal to X M1 multiply M1 plus 0.88 M3 plus 0.016 multiply 43.1. Totally you get this. That's right. Get this. And this. Right. You know M1. You know M3. You can solve for M1. You get this. And then you can balance around mixing point. That's right. Mixing point. Yes. That's right. Mixing point. Okay. A balance, M balance, and W balance. For A balance, you have to check the amount of A. A is 0.275 multiplied by M1 plus 0.09 multiplied by M3. The output is MA4. This is the A balance. And M balance is M1 multiplied M1 plus 0.88 multiplied M3 equal to M4. And also, water balance is 0.725 multiplied M1. Sorry, 0.725 minus xm1, all of this multiply m1 plus 0.03 multiply m3 equal to output mw4. That's right. You get this equation. This is for A. You know x1. Sorry, you know m1, you know m3, you can solve for ma4. You get ma4. You know m1, you know xm1, you know m3, you solve for m4. That's right. You know m1, you know xm1, you know m3, you can solve for mw4. You get this right. And then you balance around first extractor. You balance on A, M, and W also. xm4 balance for this. Input of A is 0.5 A. That's 0.5 multiplied 100 equal to MA2 plus 0.275 M1. This is for A. For W, that's right. W is 0.5 multiplied 100 equal to MW2 plus 0.725 minus M1 multiplied M1. And also finally, you must around out M. There is no M for this. M is 100 equal to X MM2 plus XM1 M1. That's right, XM1 M1. And then finally you get this. This is for A. That's right. You know M1, you can, sorry, you know MA2, you solve for M1. You know M1, you solve for MA2. For this case, you know M1, XM1, you can solve for XM2. For this case, you know M1, XM1, you can solve for MW2. You solve for it. For this case, you can solve for M1, M2, M3, that's right. M1, M2, M3, and then also the water and stone and M in extractor and mixing, but you don't know M5 and MA6, MW6, M6 because this is 5 unknown, but only 3 equation you cannot solve because it's one degree of freedom. You cannot solve for this. That's right. That's right. If you know any more question, you can solve for this, but now you cannot solve it. We must terminate the calculation at this point. That's right. Okay. See you for next lecture.